All right, in this video, what we're going to do is go over a small example where we're going to look at average stress. And so we're going to have a structure, and with that structure, we're going to calculate the average stress throughout different portions of the different members and the connections. And so hopefully that will help solidify some of the lessons that we learned in the previous lecture. So with that, here we go. Okay, so what we've got here is our in-class example on so that we can look at average stress. So remember, average stress is going to be a nicety that we can use for, if it's an axial stress, if it's towards the middle of the member and away from loading points. It's also useful for things like bearing stresses or shear stresses in bolts and pins. Keep in mind that average stress is an approximation, but for a lot of applications, it's quite a good application. So this approximation. So this is our structure that we're going to start with. So it's a relatively simple structure. So it's got this rod, which has a 20 millimeter diameter bar. And this boom, which is made out of this rectangular bar with this little clevis bit on the end. And there are 25 millimeter pins connecting all of them. And then there's this little loading yoke down here at the end, which has a 30 kilonewton load getting pulled down on it. So what we're going to do is we're going to walk through and we're going to determine what the average stress is on these members as we go through. So let me just adjust the camera here slightly, and here we go. So in-class example on average stress, we'll just leave this guy over here just as a reference. And so what you can see that I've done here is just drawn a quick free body diagram, and I've worked through the statics on it. You can feel free to do that in your own time. It's a relatively straightforward truss example. So we have the boom is 800 millimeters pin to pin, and the rod connects up 600 millimeters above the pin at A. And so if you solve for the reactions, only one reaction here because you have so you've only have a unidirectional member because you're pin and pin. So you've got 40 kilonewtons at point A, and then 40 kilonewtons and 30 kilonewtons at point C. If you look at the resultant of these, that's going to be a 50 kilonewton tension force in this rod at B and C, and there's a 40 kilonewton compression force in the boom at AB. So this is, this first part should be familiar to you. That will be things which you will have done in first year statics, where you've learned trusses. And so now we want to come to the next step. How do we know if we're likely to have a failure or not? And so what we're going to do is we're just going to work our way through these different members and these different connections and just check the average stress. So with that, we will start in the rod BC. So let's look at, find the average stress in rod BC. So we know that the force is 50 kilonewtons. So force equals 50 kilonewtons. And let's just we'll go, because this is the first example that we've really worked with this. What we'll do is we'll draw some small little diagrams to hopefully make this nice and clear. So again, with average stress, we're assuming that, anywhere away from stress concentrations, we can assume that we're going to have a nice equal stress across the face of the member. So if this is, rod BC somewhere in here, it's going to have this tension force of 50 kilonewtons, and it's going to have some average stress here, where over the entire section that average stress is equivalent. So first thing we want to do, so if we know that our average stress equals P over A, well, we have P, we have the force, simply need to find the area. So the area here for a 20 millimeter diameter, so D equals 20 millimeters, and the area for that equals 314 millimeters squared. So that's pretty straightforward. So we will have our stress in tension. We'll call this T equals T, 50 kilonewtons. We'll have, that's 50,000 newtons divided by 314 millimeters squared, and that equals 159 megapascals. Cool, well that's nice and straightforward. So now we know what the stress is in this member here. Let's look at that's throughout this midsection here. If we look closely at rod BC, we can see that the ends flatten out. And by flattening out, they're going to have a different section. So they're going to have a different area. So we know that there's going to be a different stress there. What's more is they have this hole in them to allow the pin to go through. So if our stress is going to be determined by the area of the section which can resist that stress, well, then we need to make sure that we're calculating, well, where our maximum stress is going to be? Well, that's going to be where we have the smallest area. And so that's going to be in the section kind of right here where the pin is at its maximum diameter. So we'll find it at the flat end. Stress at flat end of rod BC. And well, we'll draw that out a little bit. Again, we'll take our time on this first example, and we'll just draw some diagrams up just to kind of help illustrate the point. So I'm just going to draw really right across here, and what you'd have this. So we'd be cutting right through the middle of where that pin would be. And if we expose that, well, there's going to be some stress. And that stress, we're assuming, because we're looking at an average stress, we're assuming that it's the equal height over that whole distance. And so it's this area here in red that we're highlighting. And of course, on the opposite side, you'd have the same stress there. And then that would just sort of neck down to that rod like that. And again, because we have equal and opposite, so you've got your little stress block. Maybe you can see that just a little bit better on this end. So that would be our stress, average, stress, average, and that's the magnitude. And that's going to be resisting this 50 kilonewton load. So, um, that's our little diagram of what it looks like. So here again, all we have to do, we've got a stress, a force over an area. We know our force is going to be 50 kilonewtons, and then we really are just going to try to figure out, well, that area which is in tension, which is this red area that I've highlighted in here. So we can tell from our diagram, well, this flat end is 40 millimeters wide by 20 millimeters thick, and then it has a 25 millimeter hole taken out of it. So the area is simply 40 millimeters times 20 millimeters. Now, if you remember back to when we were talking about bearing stress, what we're doing is essentially we have this hole out here, but this curved section is not in tension. It's really, we're only taking out this projected section here. So all we need to do is subtract out the diameter times the thickness. You can think of it like this little square which is missing. So that's going to be minus 25 millimeters times 20 millimeters thick. So that's 20, and that's 40. And if you work that out, your area is 300 millimeters squared. So our stress there, stress tension over our area, equals 50,000 newtons divided by 300 millimeters squared, and that equals 167 MPa. And that's we can compare that to what our stress is over the middle of the bar. Obviously, it's a little bit higher, but it's not much, and that's one of the reasons why at the ends there you might need to thicken up any connection pieces when you do a design, because again, the whole idea is trying to keep that stress down below where it's going to be breaking. All right, well, we now have our rod. We have this area here. It's the same down at the other end. You can see the dimensions are the same, and you have the same size hole, so it's going to be the same stress because it's the same tension and the same area. So now that means we have the boom here, boom AB. You can see it's 50 millimeters tall and 30 millimeters thick. So let's just find the average stress at anywhere here along the length of boom AB. Stress in boom AB. And so we're really looking anywhere between here and here. We essentially have the following diagram where we just really have a rectangular section. And remember that, this is, that boom is in compression. So we have 40 kilonewtons of a compression load coming in. And again, we're assuming an average stress. So our stress is the same height across the cross section, and that stress is going to be pushing in compression. So that's our average stress there. The area is going to be 50 millimeters times 30 millimeters. So area equals 50 times 30, which equals 1,500 millimeters squared. And so our stress is going to be P over A equals minus 40,000 newtons over 1,500 millimeters squared. So we're using a minus because it's in compression, and that just goes with our sign convention where positive are for tension forces and we use negative for compression forces. So if we work out that stress, our stress equals negative 26.7 MPa, or we could simply say stress equals 26.7 MPa in compression. And those are equivalent there. So cool. Well, now we've found out what our stress is in really the main members here. Now we need to start looking at the connections. And so the first thing we want to look at is down here at A, where we have this member is in compression, and it's going to be pushing on this pin. So we've got to get the force, this compression force, into this reaction somehow, and it does that by pushing on the pin, and then the pin acts in shear and then pushes on this clevis. So we're going to look right here, and the way that section works is through bearing. So we want to check a bearing stress since this member is bearing on that pin. So we want to have the bearing stress at A. Again, what we'll do is we'll just draw our little diagram here just to help illustrate our point. So if this is the boom coming in, and it's got this circle here, cool. So it has this compression force of 40 kilonewtons. And what we're looking at with this bearing is how we're transferring from this beam onto this pin. So what we know our force, now the key is trying to find our area. Well, for our bearing, it's only bearing within this hole. So it's these area top and bottom aren't contributing towards being able to get this load into the pin. It all has to occur where there's a pin. And so just like so what we said in the lecture with bearing stress is we look at a projected area, and that projected area is going to be the thickness of the material and the diameter of that hole or the pin, in fact, of what it's bearing on. And so in this example, the pin and the hole are the same size, so you can assume they just have a very, very small tolerance. And so that means that the bearing is just going to be over the thickness times the diameter. And again, with bearing stress, because we're looking at an average stress, we're assuming that that's going to be an equal stress over that entire area that it acts on. So that's just a nice rectangular stress block there. So cool, we have our load, we have our area, we just need to work out some numbers, and then we know our stress. So our area is just going to be 30 millimeters, because that's our thickness, times 25 millimeters, which is the diameter of the pin, which is bearing on this hole. And so the area equals 750 millimeters squared. And then we can work out our bearing stress is going to be 40,000 newtons. We'll put a negative on there because it's in compression, divided by 750 millimeters squared, and we find that our bearing stress is 53.3 MPa. And we'll say that's in compression, which is a little redundant because bearing stress kind of by definition is in compression. So cool. Well, we've worked through our stresses in the rod, at the end of the rod, over that small area, that net area where there is that hole has been taken out, in the boom, and into the boom there. So the next end that we have to look at, well, we've got bearing on this side. We should check bearing on the other side. So we want bearing stress at B. And again, we'll just go through and draw our diagram here. And because we have this clevis, it's going to look something like this. So that's that yoke bit. And again, there's a pin, which is just going to come through here, through both of those sections. And I'll just finish our drawing up here. And there's our yoke. And so the force, again, is going to be our 40 kilonewtons in compression, and our bearing force is only going to act where we're transferring that load into this pin here. And so that's just going to be in this area here, this projected area on one side, and then the other side, because that pin sits neatly and it bears on both of those, and we're just going to assume that it bears nice and evenly. And that's a good assumption for a nice stiff pin. And as I keep saying, because it's an average stress, we're assuming that the stress block is the same height throughout, and so that means that we have the same level of stress throughout this whole bit. So our area is basically going to be the projected area of this hole. So the little thickness here times the diameter plus thickness here times the diameter. Since we're bearing on both of those, our area is area equals 2 times, so 2 times this, 20 millimeters times 25 millimeters, so 20 millimeter thickness, 25 millimeter diameter pin, and that area equals 1,000 millimeters squared. And so our bearing stress equals 40,000 newtons over 1,000 millimeters squared. Our bearing stress equals 40 MPa. All right, so now we've done all of our members. We've got force from our members. We've bared it against the pin. Now we need to see if the 3 different pins that we have, if they will work in shear. So the first one that we want to look at, let's look up at the pin up at C. So from the drawing, you can see that we only have 2 plates coming in. So this is going to act in single shear. So as this is pulling this way, the reaction's trying to pull the other way, so we're trying to get this shearing action. We only have 1 shear plane, so we're going to be acting in single shear. So let's have a look at that. So shear stress for the pin at C. All right, so we'll just draw our little diagram here. So if this is our pin, we have our shear force and our 50 kilonewton and F, so F equals 50 kilonewton. The area of the pin is just pi times the diameter squared over 4, and that equals 491 millimeters squared. And so our average stress in this pin is just going to be force divided by area. So that equals 50,000 newtons divided by 491 millimeters squared, and we get 102 megapascals. All right, so that's one pin down. We have 2 more to go. Let's look at the shear in pin at A. Shear stress, pin at A. So if C, we had 2 members which were pulling each other apart and doing this. Now at A, well, we have this clevis. So we've got 2 plates and then a plate in the middle. So you kind of have clevis like this and a plate in the middle trying to get pulled. So now we have 2 shear planes. So it is in double shear. So with pier C, it was single shear. And shear at A is double shear. So our pin, this one being 25. Again, same size pin, 25 millimeters. And but this time, we've got the 2 forces in from the clevis resisting it. So these are the bearing forces, and that's how we're trying to get this load in. So we have 40 kilonewtons coming in from the member, and we have the forces from the clevis resisting that. And we can see that pretty simple statics. These are equidistant. F equals 20 kilonewtons. And so same area as above, area equals 491 millimeters squared. So our average stress in this, area does not equal that. It equals that times 2, because we have two stresses. So we could either compare 40 kilonewtons to 2 times the area, or 20 kilonewtons times the area of the pin. So I think what we will do is we will look at the F 20 kilonewtons over that area, because remember, we can either be force over 2 times A, and that equals force over 2A. So that's all equivalent. And so we'll just look at this one for nicety. We've got 20 kilonewtons, and we've got the 491 already written out. So our average stress equals 20,000 newtons divided by 491, and that's just going to be equal to 40.7 MPa. All right. So we've got our 2 pins down. Time to look at the pin at B. So shear in pin at B. We'll make that E just a little better. So apologies there. Let's write that a little bit neater here. The pin. There we go. So this, you know, the first two were very similar to all of the previous examples which we had, where you had either single shear or double shear. But if we look at this let's look at this end view here. Well, we've got 1, 2, 3, 4, 5 different shear planes. You know, how do we deal with that? That doesn't look like anything we've ever seen before in the lecture. Is it double shear? Is it 1, 2, 3 quadruple shear? You know, how do we deal with this? Well, like anytime with structural engineering, one of the or you know, for most problems, best thing to do is sort of lay out the problem and then break it into chunks and have those chunks, you know, break it down to a component that's simple enough that you can work with it. So what we'll do, we'll just start by drawing out the pin. So if that's the pin, and let's just put the forces on it. So we know that we've got two forces down, because this is equidistant. We know that this is going just from our elementary statics. We know that we've got 15 kilonewtons in each of these arms. And that's, so, you know, F equals, you know, 1/2 Q equals 1/2 Q, where Q is 30 kilonewtons. All right, so that's the first one. Then we know that we've got the force coming in, the compression force from the boom. And that's going to land in a little bit tighter. And that's going to be, you know, again, because the boom, we can see we're equidistant here. We know that this force is just going to get split out into these two arms. So we have 1/2 F of AB equals 20 kilonewtons, and 1/2 F AB equals 20 kilonewtons. And then finally, and so these, you know, these are kind of nice. They're working, you know, this is in the you know, X direction. This is in our we'll call it the Z direction. You know, it's up and down, left and right. And then finally we have the force coming in from rod BC, which is coming at this sort of arbitrary angle. And that's going to be the force BC, and that equals 50 kilonewtons. All right, so now that we've got the forces on there, let's just sort of break this down into different components, and I like to think of it really as sort of slices with, you know, different you know, loads on, and that's, you know, similar to what you're seeing here with each of these plates. So you can think of these slices as where those plates are acting, and that's the interface that's getting sheared. So one of the first things to notice is that we have a symmetric problem. Symmetry is nice. It means we only have to figure out half of it, and then we have the other half of the answer. So Z. And so, well, let's start here. So I think the best thing to do is let's give these things some number, you know, just to give ourselves some reference. Let's call this first section D. second section, E, so D, sorry, E, D, E, G, H, I, and J. So these are our slices. So D is right at the end, E is our first slice, then G, then H, then J, then I, then J. So let's just look at the shear in this first section, DE. All right, so we'll just redraw it so it's a little bit clearer. So this is D, that's E, and we know we have a force of 15 kilonewtons pointing straight down. So for this small section to be in equilibrium, we know that we have to have a force in the equal and opposite direction. And we'll just call that PE. So you sum the forces in the Y, you know that PE equals 15 kilonewtons. All right, so we know that the shear force at this section E is 15 kilonewtons. So we know that the total area, the area of this pin doesn't change because it's a 25 millimeter diameter pin. It's the same as all of the others. We know that the area is 491 millimeters squared. So what we want to do, we know an area. If we're looking for an average stress, all we need to know is a force. Well, we want to find out, well, what's the maximum shear force? So we know 15 kilonewtons at this at joint E. Well, let's look between D and G and see if we get anything different. So between D and G, so we have that 15 kilonewton force pointing down. We also know that we have a 20 kilonewton force from AB coming in. And so the shear is going to be the resultant of these two, and we'll call that PG. So you might, the observant ones of you might have figured it out that PG is going to be 25 kilonewtons. So if we just look from sort of vector math, you know that if you've got your horizontal load of 20 kilonewtons, a vertical load of 15 kilonewtons, in order to make this in equilibrium, well, we need 25 kilonewtons, and that's a 3-4-5 triangle. So this is just working out the vectors, and then you can, the component which that works out to. So PG equals 25 kilonewtons. The other way where you can see this is if you've got 50 kilonewtons, if you look at just, well, what's the shear on either side of this 50 kilonewton load? So I'll hide it like that. Well, you know that's going to be 25 kilonewtons, 25 kilonewtons. It's kind of a double shear problem right here in the middle. And that's what we find. And because we're symmetric, we know that at I, we're going to have 15 kilonewtons, and at H, we're also going to have 25 kilonewtons. So 25 kilonewtons is our maximum shear force in this pin. So we can now determine our maximum shear stress. So tau average. Remember, this is the average across the section, not the average along the length. So tau average is 25,000 newtons divided by 491 millimeters squared, and that's going to equal 50.9 megapascal. And we're going to stop there. If you wanted to work out the stresses in the clevises, it's much the same process, but I think we've probably showed enough and kind of showed not only working through load paths and how does load get from members into connections and what are all of the steps that we have to check there, but we've also given a nice overview and a nice practice on determining average stresses. So that's going to be the end of this example.